morning. We'll begin with a quick summary of lecture number 22, but before I begin, let me just sort of highlight the items that we'll be covering in today's lecture. We'll be looking at another PDF which characterizes the channel characteristics that we observe in wireless channels. It's called the Nakagami M. Unlike the others where we took the theoretical model and then derived the statistical model, this was based on looking at experimental data and fitting it to the PDF. So basically this is a experiment based derivation, but it fits very nicely with the Rayleigh and Ricean type of statistics. So we will look at the Nakagami M distribution. We will look at the use of a tool that you are probably familiar with from your study in probability theory. That's the moment generating function. We have a very specific and a very important role for MGF, and we will just highlight that and explain why it's a very useful tool when we are looking at the BER analysis of modulation schemes in the context of wireless channels. Application of MGF will be one of the things that we along the way we will just make a comment about the bit error rate of GMSK, because that is something that we use quite extensively, and we'll just show that whatever tools that we have developed are sufficient for us to get the BER of GMSK as well. Probably the most important concept that we need to build on and develop in our understanding of wireless channels is called the WSS-US model. It stands for two components. WSS stands for wide sense stationary. The second one stands for uncorrelated scattering. And this basically describes the behavior of a wireless channel, particularly the ones that we will encounter. So WSS-US model is probably the most important concept because it links the time and frequency domain characterizations of the fading channel. Today we will just get an introduction to it and build on it in the next lecture. So that's our goal for today. Let me begin with a quick summary of the points that we have mentioned so far. So I know I'm repeating this multiple times, but it is for a very specific purpose. Fading channel, we talk about an instantaneous SNR. Okay, very important that we keep that always in mind, instantaneous SNR. The signal is fluctuating. I can set a nominal level EB by N naught, but the actual, what I'm actually going to be seeing is going to be alpha squared EB by naught. So that's a very important element. And we denote this as gamma. So the ones in red are the random variables. Blue is constant. So then we say that this is expected value of, let me be consistent with the notation, that it is the expected value of gamma, which is a random variable, but that's itself was a constant, so uppercase gamma. So when we wanted to get the BER in fading, so BER in fading, and again notice I have not specified that is BPSK, 16, QPSK or 16 QAM. Any modulation scheme characterize this as Rayleigh fading. So far we have looked at that primarily, but it can be generalized to any fading. Just in one step we will characterize that. So any modulation scheme in the presence of fading can be written as 0 to infinity, probability of error as a function of gamma, this is the performance in AWGN, and multiplied by the distribution of the SNR in that particular environment. Okay. So this is a very useful, very powerful equation which will be your starting point for any modulation scheme, any type of fading. What are the two things you will ask for? The first thing you will ask for is the performance in AWGN. Performance in AWGN, where you have a fixed SNR. So probability of error in AWGN as a function of gamma you will ask for. Second, you will say that, okay, gamma is not a fixed number anymore because of fading. I need to know the statistics. Whatever it is, Rayleigh, Ricean, Nakagami, doesn't matter. Give me the PDF of gamma. So that is f gamma of gamma. Once you have those two, you are able to get the representation in any fading system, any fading environment. So the Rayleigh fading specifically is what we have focused on, and we will continue to focus on. That's the most important one, because we are working in environments where there is non-line of sight. So under this assumption, again, this is a very important result. Always keep this in your mind, that we are dealing with an exponential PDF, gamma greater than or equal to 0. Okay, so this enabled us to get the BER expressions for the different modulation schemes. I won't repeat that, just show you the slide from yesterday. Basically, the modulation schemes that probably are of a lot of interest to us: BPSK, QPSK, and differential BPSK. The others not as important, but it just gives us a complete characterization that is helpful for us. And whenever there is a Q function, we also said that there is an approximation that is available to us. There is an upper bound which is given by 1 by root 2 pi e power minus z squared by 2 divided by z. And we found that that's a good approximation under high SNR or large values of z. Again, it's a good way to get a quick feel for what the numbers are. After this, we had looked at the derivation of Ricean fading. So we looked at the case where x and y are IID Gaussian, no longer zero mean, but with means m1 and m2, which basically gave us this set of equations, which are very, very useful for us to always keep in mind. This set of equations which says expected value of x, expected value of y, and the variances and the relationship with the variances. So this leads us to expected value of v squared, the mean of the power of the received signal, that is given by 2 sigma squared plus m1 squared plus m2 squared. Okay. Now, in case you are following along in Molish, he calls this as a squared. S squared is what is used more widely. So I have used S squared. In case you're reading, don't get confused. He has used A squared instead of S. Okay. So this then we described that there is a factor that describes the PDF called the Rice factor, ratio of S squared to 2 sigma squared. It can be more intuitively visualized as the power in the line of sight component and the power in the non-line of sight component, usually expressed in dB. Special case would be when S is equal to 0, which means K is equal to 0, then we get the Rayleigh distribution. Okay, and the actual expression for the Ricean PDF is given here, I naught being a Bessel, a special case of a Bessel function. Okay, so that is our broad classification, our understanding. We said that what is the intuitive understanding of the Ricean channel. The PDF moves to the right. What that tells me is that what that tells us is that the likelihood of higher amplitudes is higher. So this is a good thing for us. And as the Rice factor increases, then we will see more and more the channel becoming, having higher, larger amplitudes. Again, this has to be interpreted. The best way is if you actually generate it through a MATLAB plot. What are the assumptions that we are making with respect to S squared? What are the assumptions with respect to sigma squared? So again, we'll give this as a simple MATLAB exercise so that you can think about, is the scaling right? Why is this shifting to the left? But notice that the center is now moving towards where your line of sight component is going to contribute the maximum power. So it is variation about the power that is contributed by the line of sight component. So as the line of sight component increases, you'll find that the curve shifts to the right. And as the line of sight component becomes more dominant, what you will see that is the fluctuations start to reduce around that. So again, as you play with this generation of these plots, you will there's a lot that you can learn. So again, this we've just given you a set of samples of that. The actual impact is very much seen when you look at it in the time domain. Again, we will have an exercise to generate this in MATLAB. This is a Rayleigh channel. Notice the y-axis, very important, it's in dB. You have fluctuations from 0 dB to minus 25 or minus 30 dB. Significant level of fluctuation. As you increase the rise factor, notice that the fluctuations are reducing. Okay? This can also be seen in the PDF where you will find that the dominant part is going to play an important role, and any fluctuations about that, on a log scale looks, very does not look like it's going to be a threat in terms of BER. It's also good because it tells you that the amount of margin that you must allow for small scale fading, this is small scale fading, is now much significantly reduced because the level of fluctuations are not as you would see in a Rayleigh fading channel. Okay. I've asked you, recommended Molish chapter 5 as a reading assignment. Please do take it up. It's a very insightful chapter. One of the things that we will not necessarily spend time deriving is the cumulative distribution function for the Rice PDF. Okay. And of course, since the Rice PDF depends on the value of k, the CDF will also depend on k. So basically, you will not get a single CDF, but you will get a family of CDFs for the different values of k. Let me just give you an observation. Again, the more as you read it and as you, if you want to actually try to generate it, you will find that it's a very useful interpretation. So k going closer to 0, that means you're closer to Rayleigh. That's the red graph. And if you remember when we did the CDF of the Rayleigh distribution, we said that on a log-log scale it will look very linear, and this is it's very similar to a Rayleigh distribution. So what that tells us is that there is a fairly reasonable probability that you will get very low values of amplitude. That is what happens when you have a deep fade. So this is where the problem happens with the Rayleigh distribution. Now again, for k is equal to 0.3, it looks almost like Rayleigh, and maybe it's a good idea to actually plot the Rayleigh distribution. You'll find that the Rayleigh is slightly worse. It will be slightly worse than the red graph. Then you go to something which is mildly a line of sight, 3 dB. It's better than Rayleigh, but it's not substantially different. But when you start to introduce a strong line of sight component, notice that the likelihood of low values of received signal, envelope or power, does not matter, both will give you the same interpretation, is almost 0, because your CDF starts at a reasonably high value which is centered around the mean received signal power. So you can see that the CDF is very steep. CDF being very steep means what is it? Less than that value, not possible. Above that value, always guaranteed. Basically, your signal will be in that small range. So that's a good interpretation of what the Rayleigh channel does and its interpretation. Now, what was the assumption that we made about the phase of a Rayleigh fading channel coefficient? Uniformly distributed. Okay. Now, what is your expectation that would happen to the phase when you start seeing a Ricean distribution? Does it still stay uniform? What is your expectation? So basically, think of it like this. You've got signals coming from all directions. These signals that are coming from different directions are going up and down based on the fading, and then there's one line of sight component which is not changing. What is your expectation? It obviously will get perturbed from uniform distribution. It's no longer going to be uniform. It is going to be more or less, you're going to see that constant line of sight component being present. Okay? So here again, it's very insightful for us to look at the different distributions. So A equal to 0, remember A is Molish's notation for our S squared. A equal to 0 is Rayleigh. Notice that graph is straight line. It's a flat phase from minus pi to pi. Okay. Then as you increase the value of A, the line of sight component, he has taken the line of sight component to have zero phase. So basically, if you had chosen it to be 30 degrees, the peak will occur around 30 degrees. So he has chosen it to be 0. Notice that you start to see when A is equal to 1, a slight bump around 0 phase, because that means that component is starting to become more dominant with respect to the others. There is, yes, presence of signal in the other angles as well. Now, as you go to A equal to 3, you notice that the peak becomes a little bit more sharp, and as you go to A equal to 10, you get much sharper. That is more dominant than the other phase angles that are present in your system. Now, what is the value? Let me go back to this expression. What's the value of k that k equal to 0 gives me? Rayleigh. What gives me AWGN? K is equal to infinity. So basically A equal to infinity will mean k equal to infinity means it will be more or less like a straight line. The fluctuations of the Rayleigh distribution is no longer there. CDF doesn't make sense because there's no statistical part, and this one will become a straight line because basically all your energy is concentrated around the single line of sight component which has got a constant phase. Okay? So again, the entire spectrum of the distribution and the statistics that we observe in Ricean, Rayleigh being a special case of the Ricean, I hope is something that you are comfortable with. That's one of the important things that we need to take away from this discussion. Okay, so today's material will start with the Nakagami M distribution, and that is, as I mentioned, it comes from the world of experimental characterization. Nakagami M. Nakagami M PDF, okay, distribution. Now, where did this actually originate? So people try to do measurements in different kinds of channels and then try to characterize it saying, okay, it's Rayleigh or Ricean with a certain value of the Rice factor. It was found that certain environments did not match Ricean or Rayleigh. So did not match Ricean statistics for any value of k. When we say that it didn't match, it didn't give a good enough fit to the value of k. Okay. Notice I don't need to say Rayleigh because k equal to 1 is k equal to 0 is Rayleigh. So Rayleigh is a special case of Ricean. So the observed statistics did not quite fit the Ricean statistics. So they came up with a distribution which seems to have a framework very similar to the Ricean distribution, but somewhat different, and again we want to be able to capture that. So, so far the options that we had were no line of sight, means we said you take Rayleigh, that's your Rayleigh distribution, and with line of sight component it was Ricean, we had to specify the value of k. Okay, and now a third option is being given to us. So think of it as the same expression that we have for Rayleigh Ricean. So V is equal to square root of x squared plus y squared. Okay, and the Nakagami distribution does not make any specific assumptions on the mean, but it makes assumptions on the received power levels. So it says that if I introduce something called, like the k parameter, something called the fading figure, which is a characterization of the statistics, and we define the following: uppercase omega is equal to expected value of v squared, mean received mean signal power, and m is defined involving the fourth power. Okay, again we are trying to fit the statistics to observed data. So the exact origins of this formulation not documented, but the results are very useful. So expected value of v squared minus omega whole squared. Okay, omega squared means it's the square of the square value. So basically it's like doing some fourth order statistics. So m is a fading figure, it's a dimensionless quantity. Now this gives us a measure that can then be used to characterize the distribution of the envelope, and given m we can obtain the Nakagami, that's why it's called the Nakagami M distribution. It depends on the value of M. It says Nakagami M says Fv of V, that's the PDF of the received signal envelope under Nakagami M distribution, is given by 2 times gamma of M. This is not related to the SNR, and that's one of the reasons why we have used a different value. This is the gamma function. This is the Euler gamma function. Okay. Again, all of the expressions are given in the books, but it's good for us to just write it down so that we get a comfort level with that. So let me complete the PDF. M divided by omega raised to the power m, V power 2m minus 1 e power minus m V squared by omega. Okay. So, and it depends on the value of m, and m has to be greater than or equal to 1/2, and basically this is the characterization that we have, and of course v will be greater than or equal to 0. Okay. So this is the Nakagami M distribution. Let's just write down a few more points that are helpful for us to get a complete picture. The Euler gamma function, gamma of M, may have come across that in some of the digital communications. It's m minus 1 factorial. Basically, it's a factorial representation if m is an integer. It's also defined for non-integer values, so we have to be a little bit careful when they are non-integers, but most of the times we will try to find integer values. But if it is non-integer, it's good for us to know the definition. Gamma of z is given as an integral 0 through infinity e power minus t power z minus 1 dt for z greater than 0. And that's what we are going to be looking at, basically looking at the fading figure. This is called the fading figure, which is greater than or equal to half, a positive quantity greater than or equal to half, and that's what we have, and this is the basic definition of that. Okay. Now, first thing, always a few sanity checks. Let's take a look at this special case. If I set m equal to 1, I would like to look at the distribution. That's a valid fading figure. Fv of v is given by 2 times gamma of 1. Gamma of 1 is 0 factorial, which is 1. The next term, m is equal to 1 divided by omega raised to the power 1. And omega is equal to expected value of v squared. And so omega is equal to expected value of v squared. So that will be equal to 2 sigma squared, 0 mean Gaussians, okay, 2 sigma squared into v times e power minus v squared by 2 sigma squared. So basically if you rewrite this, this will come out to be v divided by sigma squared e power minus v squared by 2 sigma squared, which is Rayleigh. Okay, this is the special case of a Rayleigh distribution. Now, 2 purposes for making this observation. One is to show that the Nakagami M distribution also covers the entire span, going from Rayleigh all the way to AWGN channels. Okay, that is one aspect. And you will find that like the fading factor, like the Ricean factor, the fading figure also has a range of values. It covers the whole spectrum. And as you increase the value of m, you will find that you will start to get more and more behavior like the Ricean. So the Nakagami M and the Ricean are like equivalent representations. But there's a very, very important difference. What is the worst case that you can get in Ricean fading? Worst case, Rayleigh. Okay. Notice that that's not yet the worst case for Nakagami M, because M equal to 1, you can actually get certain environments which look worse than Ricean. You may ask, is it possible? We already thought Ricean was bad enough. But yes, there are certain environments where the propagation is worse than Ricean, and even those scenarios are actually captured by the Nakagami M. Okay. Now, you may or may not encounter them, but it's good to know. So let's build on this a little bit more. So summary, Nakagami M is a very useful form. You have to specify the value of M, and then the PDF is specified. M equal to 1 is Rayleigh. M greater than 1 is milder than Rayleigh. That is less severe than Rayleigh. And there are scenarios where M is less than 1, which is more severe. Okay, so just keep that characterization in your mind. Therefore, it's good to know that this is a family of functions. Another important thing that we probably need to make note of is look at the PDF of the Nakagami M distribution. Has no Bessel function. So actually it's easier when you want to do integration. So that's the second reason why we prefer the Nakagami M. But from a understanding point of view, Ricean is very intuitive because it says there's the power of the line of sight component, the non-line of sight component. So the question that arises is there a way to map the Ricean distribution to the Nakagami M? And it turns out that yes, there is a way to do that. So Nakagami M can be mapped to the Ricean PDF. Ricean PDF. Okay, for that we have to choose the following. We have to choose the value of M. We have to choose the value of omega. Basically, that's the, and this will map to a particular value of K. So basically, on the Nakagami M side, we have to specify something. On the Ricean side, we have to specify, and then we have to make the relationship. Okay. So the relationship I will give you, it is derived in the literature, but again it's more important for us to know that it can be mapped. So M is equal to K plus 1 whole squared divided by 2K plus 1. So if I gave you a value of K and said my channel behaves like a Ricean channel with this particular value of K, not a problem. You will just do a simple calculation to get the value of M and then substitute it and do all of your computations of the BER using the value of M, because that's easier for us in terms of the integration. So if you can relate M to K, you should be able to relate K to M. Please verify that if this is given to us, that the inverse relationship is given by 2 square root of M squared minus M divided by M minus square root of M squared minus M. Again, it's just to say that you can go from one domain to the other, but you cannot get a mapping for those functions which have the fading coefficient M less than 1. Okay, so please make sure that fading figure less than 1, because those are the ones which are very unique to the Nakagami M distribution. But again, this is something that we may encounter in experiment using when you do experiments. So we have the following tools available to us. We can characterize the environment. Very often, what we encounter is Rayleigh distributed. So the SNR distribution F gamma of gamma is given by an exponential distribution. Okay, and otherwise, if it's not, there is a line of sight component, it will be Rayleigh. Rayleigh means that it will be Ricean, it will have a Rice factor. Once you get the Rice factor, you can map it to the Nakagami M parameter, and then that says that, okay, there is a corresponding SNR in the Nakagami M. So what is the PDF of the SNR in a Nakagami M environment? That's very important to us, and this is something that we will derive as part of the assignment. But let me just give you that there is an expression that is easy for us to validate, and that is given by m by omega raised to the power m gamma power m minus 1 divided by gamma power m e power minus m gamma by omega. Okay, and we can go through and validate that gamma, what we have used in the Rayleigh environment, is the same as omega. So that's easy for us to verify, and you substitute m equal to 1, we should get back the Rayleigh distribution. But this is the SNR distribution in a Nakagami M environment. So if you were asked to compute the probability of bit error, so let's go back to the first equation. The probability of error of gamma, that is AWGN. Now for the second term, if it is Nakagami M, you will now substitute the corresponding Nakagami M PDF and then complete your integration so that you will get the result that is of interest to us. Okay. So what we have built around is different tiles that help us to get a complete understanding in terms of insight, in terms of the ability to characterize using analytical tools, and then and work with the different environments. We now will move into the second part of what I had mentioned today as the moment generating functions, usually denoted by the acronym MGF. Again, this is a tool that most students are quite familiar with from the mathematics concept. Maybe you, when you were studying MGF, you thought, why do I even study this? Is there any use for MGF? Today we'll answer that question. It's actually very good that you have studied MGF before, because we have a lot of use for that. So let me start with the basic definition and then build on that. I will, as always, I'll just give you enough information to understand the concept, apply it, and then go back to give you the complete definition. Okay, so let me just, okay, this is MGF. The definition of MGF is, MGF by this is defined for a PDF. So let's assume that we are given a random variable x and the PDF of, so the PDF of a random variable x is fx of x. Then the moment generating function, different books use different notations. I would like to use psi as my notation for moment generating function. Subscript tells you the random variable, and it is usually given in terms of a parameter s. And you may wonder, does this mean you are doing Laplace transform? The answer is yes, it's kind of a Laplace transform. I'm sure most of you see many of you nodding. But we have to interpret it. Basically, s is just a variable. This is given as minus infinity to infinity, and over the range of the random variable x, fx of x, e of sx dx. That's a definition of a moment generating function. Okay. Now, a couple of key interpretations. Again, the first interpretation is from the mathematics point of view. The second one is the electrical engineering point of view. It says, okay, I want to look at it as a Laplace transform. The first one is a mathematical interpretation. Mathematical interpretation says you took some function of x, multiplied it with the probability distribution of x, and then integrated it. So what did you do? I computed the expected value. That's a mathematical expression, e power sx. So the mathematics interpretation of this equation says that you calculated the expected value of the function e of sx. Okay. The electrical engineering definition says, well, you almost did the Laplace transform except the sign was wrong. So basically, if you do replace x with minus s, then you have actually computed the Laplace transform of fx of x. Okay. Now, which of these is more useful? Both are useful. We will use both of them. The good thing is that the moment generating functions have been already computed for the PDFs that we will encounter. So I would encourage you, that's why I have given Andrea Goldsmith book as a reference, Goldsmith chapter 3, where you can find the moment generating functions of the Rayleigh distribution. You can also find it for the Ricean distribution. It's a little bit tricky, the Ricean distribution, and you can also find it for the Nakagami M. So it turns out that the distribution that we are interested in are already characterized for us in terms of the Laplace in terms of the moment generating functions. But before we even do that, why even bother with the moment generating functions? Let me give you an example and then show you why it is very powerful for us. Okay, so we want to look at the case of the Rayleigh distribution, Rayleigh PDF. The moment generating function is what we are asked to evaluate. F gamma of gamma is given by, this is the PDF of the SNR, e power minus gamma by gamma. If gamma is greater than or equal to 0, otherwise. So when I do the moment generating function, I'll write phi, my subscript will be gamma and it will be S. My limits of integration, since it's the PDF is non-zero only for in the range 0 to infinity, 0 to infinity, 1 over gamma e power minus gamma by gamma, that's the PDF part, and then I write down E of S gamma d gamma. Okay? Moment generating function of Rayleigh distribution is given by this. 1 over gamma is a constant, integral 0 to infinity e power minus 1 by gamma minus S into gamma d gamma. Now S can be in the complex plane. So I have not necessarily assumed it to be real valued. So basically, I have an integral of this form. What is the condition for this integral to converge? What is the condition for the integrand not to explode? Because gamma will go all the way to infinity. So the 1 by gamma minus S, the real part must be less than 0. Okay. So must be greater than 0. Okay, okay, you're paying attention. Okay, the real part of 1 by gamma minus S must be greater than 0, which is the same as gamma is already a real quantity. So real part of S is less than 1 by gamma. Okay, so just a visualization. This is the complex plane. If this is 1 by gamma, we are saying that everywhere here we are okay. That's sort of the region of convergence that we have, if you will. So in this region of convergence, I get the expression 1 over 1 minus gamma S. And that's the moment generating function of the Rayleigh distribution. Again, keeping in mind that there is a ROC that we have to keep track of. It's not a problem. Okay, so let me just remove the clutter and write down the following. So phi gamma of S for a Rayleigh PDF is given by 1 over 1 minus gamma S. Okay. So the question is, what is the benefit of this? We see in a minute. So if I were to compute probability of error of dBPSK in Rayleigh fading. Okay, please tell me the expression. It will be 0 to infinity. The probability of error in AWGN will be half e power minus gamma. Am I right? That's the probability of error of dBPSK in AWGN. Then write down next to it the PDF of the SNR. So the PDF of SNR will be f of gamma integrate with respect to d gamma. Okay. Now, side by side, please write down the expression for the moment generating function, and then we are through. This is 0 to infinity f gamma of gamma e power s gamma d gamma, and this we already know is 1 minus gamma s. Okay. So, the question is, do I really need to do the integral at all? The integral is very easy to do. It's not that it's because the reason is that once I have this expression, you can see that this is nothing but the constant. You pull it out. Now look at what is within the bracket, equation number 1 and equation number 2. Compare them. You can confirm that this is nothing but phi gamma of s, where s is evaluated at -1. Now, is s in the region of s equal to -1 in the region of convergence? Yes, because it's the left half plane including the j omega axis, no problem. So, this is where the so now the important thing to note is you can change this f gamma to anything, even Ricean, no problem. Ricean or Nakagami M does not matter at all as long as I know phi gamma of s. Any distribution you tell me, as long as you give me the moment generating function, I will give you the answer in one step. I'll just substitute the corresponding value and we'll get the answer that is of interest. Okay? So, this is why MGF is so useful, because it is very, it helps us in terms of our ability to work with the different types of environments that we are looking at. Okay, so let me just move forward quickly to explain one more example. Okay, this is an example not related to MGF or the PDF. It's something that reinforces what we have studied so far. GMSK stands for Gaussian minimum shift keying, so I won't expand it. Usually when you specify Gaussian filter, you must also specify the shape of the filter or the bandwidth of the filter. It's usually given in terms of a parameter called the BT, the time bandwidth product, and BT 0.3 is the commonly used value. I will make a couple of statements about GMSK BT 0.3. Again, this is for you to just keep in mind. When we come across it later on, we will talk about that. BT 0.3, it comes under the family of what is called partial response signaling. Partial response signaling. What is partial response signaling? What is full response signaling? If you know full response, you will be able to. What is not full response becomes partial response. Okay, full response. Okay. Pulse shaping, everyone is familiar with. Why do you do pulse shaping? To keep the spectrum very compact. Now, once you have done the pulse shaping, you have a symbol duration. So, Ts is your duration of the symbol. Okay, that is, you have the symbol rate, 1 over the symbol rate is the duration of a symbol. Now, if your pulse shape, duration of the pulse, so basically if I were to use a rectangular pulse 0 to Ts, that is full response. I can do a sinusoidal thing between 0 to 2s, that is also full response. This is full response, this is full response. If the duration of pulse is less than or equal to Ts, it comes under full response. Now, if I have for some reason, I have a pulse shape which exceeds Ts, let us say 0 to Ts, it goes a little bit outside of Ts. This becomes partial response. Partial response, what's the penalty that I'm paying for partial response? Why do I do partial response first of all? To make the spectrum more compact, because more I have wider in time, narrower in frequency. So, it's more compact in terms of spectrum. So, the reason we even talk about partial response is because of the benefits in terms of spectrum. But what does it do in the time domain? It already introduces ISA at the transmitter. Whether the channel causes ISA or not, your transmitter has caused it. So, there is transmit ISI. Now what will happen if you have ISI in the channel? That ISI in the transmitter will get compounded by the ISI in the channel, and you will get a composite ISI which you will have to equalize. Even if you do not have ISI in the channel, you still need an equalizer. Okay, so this one requires an equalizer to get rid of the intersymbol interference that you have introduced through the partial response. So again, we need not worry so much except to make the observation that complexity is going to go up. Okay, complexity is higher than if you did a full response system. So that is all that we need to understand in terms of the partial response. So partial response signaling basically says it's ISI is there in the transmitter for the purposes of spectrum. Complexity will be higher, we will live with that. Okay, but now given that GMSK BT.3 is a partial response signaling, the question is, what is the probability of error of GMSK? People have characterized this and have said it can be very closely approximated by 1.4 gamma, Q of 1.4 gamma. Notice that there were two Q functions. We'll take the BPSK case, it was square root of 2 gamma. Now is GMSK better than BPSK or worse than BPSK? The way to look at it is, if I were to specify a given BER level, that corresponds to some SNR. So basically from the Q function you can find out that 2 times gamma BPSK, which is what that's what will give you that BER Q function, that will map to 1.4 times gamma GMSK. Right? Because the Q functions, the argument of the Q functions map to the same BER value. So for a given BER, and if I want to satisfy it with both BPSK and GMSK, I must satisfy this condition. So this clearly tells me that gamma GMSK is higher than gamma BPSK. So that is gamma BPSK plus 1.55 dB. So it is slightly worse than BPSK, but it is something that is better than the non-coherent schemes. So therefore, this is a useful candidate, especially because the spectrum is very compact. Okay. Now let's complete the discussion. Just one more observation that I will give you. Now, if I had the relationship for BPSK, Q of 2 gamma, that is in AWGN, in fading we said that this maps to 1/2 of 1 minus square root of gamma divided by 1 plus gamma, and under high SNR this maps to 1/4 gamma. Now without redoing all of the calculations, can we get the expression for GMSK, where GMSK is equal to square root of beta gamma, where beta is not 2 but is equal to 1.4. So we have already done a case like this. So basically what we would like to do is, in this expression, replace gamma with beta by 2 gamma. Right? So basically get it into the form. If I do this kind of scaling where beta is a constant, 2 is a constant, so there is no issue with that, then in this graph I would have to do the scaling gamma as beta by 2 gamma, and then redo the calculations. We do not need to do the integration. This will become 1/2 of 1 minus beta by 2 gamma under the root sign divided by 1 plus beta by 2 gamma. Okay. Again, you can simplify that. You can also verify the high SNR approximation comes out to be 1 by 2 beta gamma, which is the same as 1 by 2.8 gamma. It is not as good as asymptotically. It will not touch the BPSK. It will always be shifted, slightly worse, but it's a very good modulation for us to work with. On the other hand, dBPSK the asymptotic value is 1 over 2 gamma. So which means that the dBPSK is slightly worse than GMSK, and so we can make the following statement, which I believe is correct under assumptions. So in Rayleigh fading, when there is no channel tracking errors, the BER of BPSK is less than BER of GMSK is less than BER of dBPSK. Okay, and since I need equalization, there is no question of non-coherent detection of GMSK. It has to be coherent. So this has to be coherent detection. This has to be coherent detection. Okay. So again, this was a little bit of a detour, but to tell you that the tools that we have developed are very broad and very useful. Now combine the tools that we have developed with the moment generating function, you have all the tools that you have need for understanding and working with the BER expression. So what I would like you to do is refresh your memories about the MGF. If you have recently studied it, no problem. If you have not studied it recently, look it up in Proekis or any of the standard books. We will use MGF in some very clever ways just to help us understand and derive the bit error rate in fading environments. With that, we will then move to WSS-US model in the next lecture. Thank you.